Yeah, to base 2. So change the 64 to base 2. And you just left it on the bottom for now?
Sorry for the interruption. Any students that are going with Mr. Kinnear to the law course building, they will be leaving from
2 to the
the
6,
entrance
right?
by the office in 5 minutes. Once again, reminder to all students participating in Mr. Kinnear's class and or the law course, you must be within the hallway here by the office, lawn entrance doors within 5 minutes. Thank you.
So if I get 6 times x over 2, it becomes 3x, okay? So far so good? And then what I do is I bring the 2 up, right, upstairs, I guess. So it'll be a negative 3x. And then finally I have these guys equal. So I have negative x minus 5 equals minus 3x. I could bring the 3 over to get a positive 2x equals 5. So x equals 5 halves. 5 over 2, 2.5. Perfect. Okay, that was solving an exponential equation, correct? So, sort of a simpler one because we could convert it to same base, right? Then now we have a logarithmic equation. I know there were a few people who got an answer for this one. Any volunteers for doing this question or describing how to do it? Yeah? You want to describe, John? Yeah. So you used the power rule, right? To put the 2, and then just recorded the rest? Why did you do that? That's a good move. Why did you do that? Yeah. Sorry, that's not a little x, that's a big X up here. Yeah, the base is 10, right? That looked like a base down there. Okay, and basically, you got to put that 2 as an exponent because you can't use the laws of logs with coefficients in them, right? There's no coefficients. I want to squish these 2 together. I think that's your game plan. So put them together, and how do they move together? Subtraction becomes a division statement. When I put 2 logs together, 2 logs become 1. There's only 1 log, right? And then this side stays the same. Now there's 2 paths I can go. What did you do next? Okay, sorry, what did you do? Base. So you just kind of did this, right? Yeah. Same base, so I can just use that same base technique. 2x minus 3. Then I multiply, so I get x squared equals x plus 2 times 2x minus 3. And as we've seen many times, a quadratic will develop, right? 2x squared minus 3 plus 2 is a negative x minus 6, right? Now it's a quadratic, so I combine like terms. That gives me x squared. What did I get? 2x squared minus 3 plus 2. Oh, so thank you. Thanks, Eileen. Okay, bring the x over, so that allows me to, what is it, a 3 and a 2? Okay, so these are very important. I have to check my answers in the arguments. The arguments can't be negative. So the negative 3 will not work, right? Because negative 3 plus 2 gives me a negative here. So this is not going to work. The 2 will work, right? So my answer is only x plus 2. And show that you've slashed out your extraneous root. Okay? How are we doing so far? All right, last question, the toughest of them all, right? This is tough because it's exponential and I can't do same base approach, right? So the first thing I do is log both sides, agreed? By taking logs of both sides, that allows me to treat the exponents then as coefficients. So they come down as coefficients. These are the long ones, right? The ones that have x's on both sides. There's really no short way to do it. I have to multiply through, then group my x's. So I multiply through to get rid of the brackets, right? 3x log 11 minus log 11. And do the same thing you've done with other equations, just simple linear equations. Anything with an x goes to one side. So I'll bring this term over. And anything without an x goes to the other side, right? You could have switched sides. It might have been better, less negatives. But now what I do is I factor the x out. And that isolates my x finally. There's lots of rewriting in these, right? And then I want to cancel this out. So how I do that is I divide it out from both sides. So I get this monster that I have to punch into my calculator, right? That's why you really have to have a calculator you can rely on. Now, because we have a complex fraction here, right? More than one term on top and bottom. Very complicated to type in. My calculator gives me problems all the time because I have all those double brackets that I have to deal with, right? So let's see. I know what I'm supposed to get. Minus log, bracket. Minus log 11, I have to close my bracket. Minus 2 log 6, close two brackets, divided by bracket, log 6, minus 3 log 11. Okay, so I get x equals 1.107. I saw a few of those around there, right? Good for you if you got that one. That's the most complex it can get. So if you have an understanding of these three types of questions, like I said, just knowing this, you should be able to pass the test for sure. And then as well as combined with all the other little intricacies. All right, we've got one last job to do here. And so it's nice that this is Wednesday because we've got a couple of days to work on these. We're going to do our word problems, the applications, which this is the section I would say that has the most varied types of word problems, is the logs and exponents. Because the logs and exponents themselves, they're sort of, you kind of attack them in different ways. So the applications can look different. Now, I'm kind of impressed by this textbook for how they outline the different types of application problems, right? And I'm on page 253. So this is something worth your while to maybe peruse, to scan through over the evening maybe, or over the weekend even. It does give lots of guidance. I'm going to go through our examples that we have made up for you from the examples booklet. But here they actually explain, they give you examples, more examples of type. This is an explanation. They're telling you how exponential functions are basically a sequence of numbers, like looking for patterns. And then that leads you to one of the formulas that you'll commonly see. This is a formula for exponential growth. So you'll get used to seeing this. Take a look at this and you can kind of see what's happening here, right? You've got a base. You've got a vertical stretch, which affects the y-intercept, right? And then you've got a variable in the exponent. So this is an exponential equation, right? Unknown in the exponent. We're going to see a lot of these in the applications. And we've seen this before. Remember on assignment 1? This is a variation of that. Now this formula, I will give you the formula in your exam. On your test. And in the final exam always for this particular unit, they always give you the formula to use, which is kind of nice of them. So that's the format I'm going to follow on your test on Monday. I'll give you, if there's a formula to use, I'll give you the formula. You have to be able to set the formula up, though, with the numbers from the question, if that makes sense. Right? So if I ask you to do compound interest, I'll give you this formula. You have to know what all the pieces mean, though, right? So those are two examples of exponential equations. Then there's a logarithmic. Remember we talked about the Richter scale is a log scale? So again, this is a common type of formula. Usually you're given it in this form. And what does this represent? Well, I is the intensity of one earthquake to another. So quite often you're asked to compare one earthquake to another. And we said, I've mentioned a couple of times, those numbers on the Richter scale, the Richters went from, I think it can go up, it used to go up to 1 to 10, but I think now we've had earthquakes higher than 10. But an earthquake of 7, an earthquake of 10, what those mean are, the Earth's tremors are actually 10 to the power of 7, 10 to the power of 10. So a movement of 1 on the Richter scale is actually a power of 10 move, not 1. It's not moving up one number, like or 1 inch or 1 decimal, it's moving up 10 times, okay? Now, many of you also said that you used logarithmic scales in pH in chemistry. So you might see a pH problem appear, but once again, because this is such a varied unit, you'll always be given the formula to use in my tests and exams. This booklet doesn't set the formulas up for you. So when you get to do your assignment today, I'm going to assign a few questions. When they're talking about a pH question, just look back and look at the formula they used, right? They've identified them. Another place you'll see a log scale is in sound, right? Which makes sense because sound is similar to like the tremors of an earthquake. It's that movement, right? So again, sound is measured in decibels, and it's a logarithmic scale. So here's the decibel scale. And it's kind of interesting, right? Now this is a power 10 chart, right? But it says, it doesn't give you the formula there. But the difference between 0 on the decibel scale, which is the threshold of hearing, to a whisper, is a difference of 25 on the decibel scale, right? And then it keeps going up and up and up and up. Jet engine is 145, okay? And this is the formula that compares these schedules, or these levels again. Again, see that base 10? And this is a type of question you might be asked, and we'll do one of these for examples today. How many more times intense is the sound of conversation at 71 decibels than leaves rustling at 12 decibels? So just numerically, if you were to subtract 71 minus 12, you'd think it's just a difference of, it's just a difference of 59 on the decibel scale. That doesn't mean much. It's actually about 800,000 times more intense conversation is, like someone talking, than leaves rustling. Right? That tells you how powerful these scales are. So they've got lots of examples, and if you look, I kind of breezed by, but they've done an example for compound interest. They've done an example for Richter scale. They've done an example for pH. I'm not going to going over these ones because you can look at them yourselves. They've done a couple for intensity of sound. And these, we're going to have to see a lot of these. Now we're into, those were logarithmic scales, and now we're back to some exponential equations. This is the general formula for growth and decay in nature. Okay? And that's an exponential function. And again, you'll be given this formula, but look what you see here. What do your eyes see? Anything interesting here in this formula? What's the base? Right here, E. E is the base, right? That's how many things grow in nature. They grow at that base E rate. So what types of things grow and decay in nature? Well, bacteria, radioactivity, again, for those science people in chem. That's one of the ways that they can identify different elements, right? Is how radioactive they are and how long it takes them to decay. And you'll see a lot of words talking with half-life. The half-life of a substance, that's something that's used in chemistry. So if they put a certain amount of radioactive material in a dish and they observe it, half-life is the amount of time it takes for it to disintegrate or decay to half its original amount. So if I start off with 10 grams of some type of substance, however long it takes to decay to 5 grams, that's its half-life. And every element has a unique half-life just associated with itself, so that's another way they identify these elements or substances, right? Just like on the periodic table, how they all have their own atomic number, right? And the half-life is another way for the radioactive ones. Okay, so there's a lot, you can see there's tons for us to do here. It's going to take us a few days, I think, a couple of days to maybe get through these. I'm going to assign some of these questions, but like I say, they don't, unfortunately in here, they don't give you the formula embedded in the question, but here it says compound interest, right? Or compound annually, so that's your cue to, oh, I got to use the compound interest formula. Here they actually give you the formula, which is nice, but on some of these they don't, right? But here, if they're talking about normal conversation, just flip to the example with the normal conversation and you'll find the formula, okay? Now, you can also probably use some of the examples that we're going to talk about today, because I have embedded the formulas into our today's examples. So we're on page, something got screwed up with the printing. We're on page 27. We're going to do our first application. Okay, so page 27. There are many applications of exponential and logs. Like I say, this is the heaviest word problem unit we'll do in this course. Some problems that involve the application of logs and exponents involve growth rates of populations, radioactive decay, compound interest, pH, Richter. So we had just seen those. So we're going to do, I think I have one of each of these in here. A country's population is growing at the rate of 3% annually. Assuming that the population is now 30 million, use the formula A equals PERT to answer the following. What will the population be in 15 years? How long will it take for the population to double? What assumptions are we making? Okay, so again, in these examples, I believe I've embedded the formula in every one of them because it's sort of similar to what they'll do on the exam. This is my formula, A equals PERT, but I'm just going to identify the pieces for you. Again, we see the natural growth rate, right? So this is just the natural growth rate. Natural growth base, we'll call it. And we know about 2.72, right? But we use the E button on our calculator, right? P, does anyone know what P stands for in any of your previous work or what I mentioned maybe when we were talking about compound interest? Present value, right? I'll use the word present value because that's a good way to remember it, because the P for present value. Some people also think of it as it's the initial amount. Did you have another definition, Neville? Is that? Yeah. Yeah, so initial amount, present value, because usually we think of value as money, but the initial amount. So what's A? If P is the initial, what's A? The final amount. Now, if I'm talking about a population growth, this would be what the population started at, right? This is what the population ended at the end of my studies.
So if we're saying A, is that like the future value that we're going to say?
Perfect.
Just to understand.
Just to keep it in context with what you set up here, yeah. Now, but if we were talking about a bacteria that we're growing every hour, then for this time would be number of hours, right, for this formula. Okay, so let's start answering the questions. What will the population be in 15 years? Okay, well, what do we have here? The population is now 30 million, so P is 30 million, right? What do we have? Country's growth rate is 3%, so that's R, isn't it? Notice what I'm doing here. We don't put percents in formulas. We only ever use decimals only number. What else do I need? I know what E is. T is 15, right? And I know what E is. E is about 2.72. So I know PERT, so we're finding A, right? There should only be one unknown in a math statement. So A equals I'm just gonna leave it as 30 because I don't even think my calculator can hold all the zeros. So if I just leave it as 30 and I know that my answer will be in millions, right? Then I'll just have to make sure I record my answer as millions. E is a button on your calculator. You must use E. I only did this to put this in context. Do not use 2.72. You won't get the correct final answer. Now, we have two exponents, right? So I would suggest I don't know how your calculator works. Some of them are easier than others. I would suggest when you have two exponents to use brackets. Okay, you can see if you ever had this as an exam question, you would definitely have this on the calculator section, right? So 30 times E to the exponent, 0.03 times 15. Give it a try in your calculator too, because these can be tricky. And it's 47. I'm going to say, because I'm answering like they gave me in the question, like they just left it as 30 million, I'm going to say it's 47.049. I'll do the 3 decimals, but I'll just say million. Or you could have done this, you could have multiplied by 1,000,000. 1, 2, 3, I think that's it, right? And you could have recorded like that. But I decided to give them the answer back like they gave it to me, the info, if that makes sense. Not so hard, right? Okay. How long will it take for the population to double? How long? What are we solving for here? Find T. Okay. Now, I'm just going to add here, because I think when I did this once, there's a bit of confusion. I'm just going to add this from times 0, because some students were thinking, oh, double from this amount. But when it was written, the assumption was double from times 0. So the initial population's 30 million. If all I have to do is find T, then I must know what P is. I must know what R is. I must know E, of course. We know E. Means I must know what A is if I have to find T, right? I should know everything else. So P again, I'm just assuming it's 30 million. The rate is, I guess it's 0.03, right? We haven't been told otherwise. E is a number. What is A? 60, right? It must be 60 million if they said it was double. Okay, so I put my pieces in. 60 equals 30 E 0.03 T. Okay, can you see why this is in the logs and exponents unit? Because it's an exponential equation, right? Using x's up there, a t and x, it doesn't matter what letter of the alphabet we use, it's an unknown exponent. So therefore, it doesn't look like I can use the same base. Is there anything I can do before I take logs of both sides? Divide by 30. So that gives me a nice 2. That's much easier. Okay, I got to take logs of both sides, but I want to be strategic here. Any ideas? Yeah, I would take the natural log, right? I could take either, and they'll both work. But if I lned both sides, it saves me quite a bit of work. Once again, you could log, that's fine. It'll just take you another step. Because we know that ln of E, that's going to cancel to 1, right? But I don't want to cancel it out till I bring my exponent down. That was the whole purpose of lnning. Okay, so once again, ln of E is 1, because if this is my base to the power 1, equal E. So that's gone. So that becomes quite straightforward then. Ln of 2 divided by 0.03 is equal to T. So in your calculator, so T equals, anyone want to give me an answer? 23. And let's answer to 3 decimal places. Let's get used to 3 decimal places. Right? So in 23 years, this country's population will double. All right. I guess we left the blank page next to answer the next question. Part C, this is important too. What assumption are we making? There might be more than one. Yeah, that's the big assumption, right? We are assuming that the growth rate stays steady, right? At 3%. I'll throw another question at you that's kind of involved with this type. What might affect a growth rate? What can affect the growth rate? Birth and death rates. Maybe you have all of a sudden a birth explosion, or a lot of people die. Immigration. Lots of people immigrating will grow your population, right? So things like that. Okay, not so bad, right? The setup is the hard part. The solving is probably pretty straightforward to you. You've done much more complicated than that. It's the setting up though, right? So let's look at example 2. There was a nest with 200 wasps. If the rate of increase was 0.015, so that's nice, they already gave it to us in decimals only. How many days, so this time is in days, how many days did it take for the population to double? Use the formula, so once again they give you the formula. Okay, so I think you could try this one on your own because it's, it's the same type of question. So give that one a try. it looks like most people set it up yet. Try the next one too. Make sure it's business days. Or this days. Yeah, just put it. I'll do that right now, I think. I'll look at this one, then we'll look at the decay, and then I'll let you guys go for a break, and then I wouldn't mind finishing the word problem so you can do a little of homework tonight. Okay. Student. Okay, where is the calendar? That's weird. I think we're back on the 6th, Ibby, but let's see. Yeah, it's the 6th. Okay, I think everyone's had time to try. So we have, okay, what do I need? I need I've got A, P, E, R, T. Maybe I'll list them that way. So do I know what is the 200? There was a nest with 200 wasps. 200 is the P. E is a button in your calculator, right? I'll just put down calculator. What's R? Thank you. And what's the time? That's what we're trying to find, right? So that means I must know what A is. So all it says, I only see one number here, but it says how many days did it take for it to double? So that must mean that A is 400. Agreed? So again, I get this 400 equals 200 E 0.015 T. Okay, so that looks very similar. I divide by 200, I get my 2 again. By the way, anytime you have something doubling, you're always going to end up with 2 on the other side. Have you know, like if I had, 500 people and they doubled to 1,000. 1,000 divided by 500, we're going to get that 2. And then I have my 0.15 T. I would choose to ln. Again, did anyone log? Because you'll get the same answer. It's just a little quicker if you do lns. So anytime you see E's, I would ln. Okay, so I bring that down as a coefficient now. 0.15 T ln E, cancel. So T equals ln of 2 divided by 0.15. Let's see what I get here. Ln 2 divided by 0.015. And I get 46 point, and I'm just going to keep rounding to 3 decimals unless I'm told otherwise. 210, right? And what is my unit of measure? Days. Okay?
If 210, is that okay to write last one, 0, 22
Like this one? Yeah, probably, that would be okay, I think. No, I think you should record it in this case, because it came from a rounding. Record it. The only time you wouldn't write down 3 decimals is if it was something like if it's 3 decimals and you just got that clean, you don't have to write the 0. But because it came from rounding, I would record it. All right, let's try a radioactive decay, because it's the same type, it's the same formula. Can you see? But it's a decay. So what do you notice about, they actually gave us the formula. They gave us the rate. Notice that it's, what happens when something is decaying? You get a negative rate. That makes sense, right? Okay, a radioactive substance is decaying according to this formula, and they actually gave us the rate right in the formula this time. That was nice. A is the amount of material remaining, T is years, P is initial amount, which was 80 grams. How much remains after 3 years? Okay, so I got A, P, E, R, and T. E is in my calculator, right? R is negative 0.2, that was given. Initial amount is 80. 3 is years, and this time it is in years, so I'm finding A, right? That's the easiest one to find, because the formula is given, it's all set up to find A. So that's really straightforward, this one. Right? Just knowing how to put a negative exponent in your calculator. So 80 times E exponent, negative 0.2 times 3, and I got 43.905. Agreement? Okay. So A equals 43.905 grams. So in this case, because the substance decayed, did you notice you started with 80, it decayed to 43? Questions? They're not hard, right? Now that you know how to solve exponentials, I think the logarithmic ones are a little stranger, to be honest, because we don't have as much experience with logs. So I'll let you guys go for a break right after I do this, and then we'll do a couple of log ones. We'll do a compound interest and a couple of logs. What about part B? Determine the half-life of this substance. Now, it's very similar to being told that the population doubles, right? It's just the reverse of that. So think of it this way. You start off with an initial amount. Half-life is when the amount becomes half of what you started with. That's all that means, right? Half-life, I know it says the word life in it, but it's basically referring to a quantity. This is when the initial amount is half of what you started with. Now, it's still, it kind of makes sense in a way. They're saying, what is the half-life? So it's referring to time, right? So you're still solving for T. Because it's the time it takes for the initial amount to disintegrate to half of what it was. Okay? So determine the half-life, you're solving for time, but the setup is the initial amount, and then when does the initial amount become half? I think the only time they use that term half-life, though, is referring to chemical substances. If it was a population, they would actually say, when did the population die off to half of what it was? All right, so how do we set this up? What are we going to set it up as? I've got my A, my P, my E, my R, my T. I know T is what I'm trying to find this time. My P was 80. E is in my calculator. The rate is the same, negative 0.2. What's my A this time? 40. And you know how we always get 2 for the doubling, like when population doubled? Or if the population ever tripled, you'd get a 3, right? You end with a 3. You know what we're gonna end up here? No, not 1. Half. Okay? Half-life? Half. Double means 2, half-life means half. So you'll get 40 over 80, right? Which always simplifies to a half. I think I'd probably record it as 0.5. Because you're using a calculator, 0.5 is a more calculator-friendly number. Okay, I'll let you guys take it away and do the rest. I'll give you a minute or two to do that, and then I'll record the answer. In the meantime, once you're done, go for a break if you need one. Maybe at about between 1/4 and 20 after, I'll finish off the last few examples.